All right, let's review chapter 4. This was a big one. We covered a lot of things. So let's just go look at the big picture for these topics that we covered. First thing we talked about the mean value theorem. And the idea for the mean value theorem is if you look at some closed interval, so let's say from A to B, if you were to find the slope of that secant line, there is somewhere on this function where the slope is the same as the slope of that secant line, and that's what we're calling f prime of c. So we're looking for what x value gives me the average for that particular interval. And again, we're not looking at the whole function, we're just looking from a to b. So we find the slope of that secant line, and I want to know somewhere on here there's a value, there's an x value, where the slope is going to be the same as that secant line, and that's what we're looking for. We're looking for C. Rolle's theorem was just a very specific case of the mean value theorem. Rolle's theorem was when A and B are the same value, right? So the mean value theorem is still the same thing, right? The slope of that secant line is 0, so we're looking for where f prime of C is equal to 0, right? So it's the same thing as the mean value theorem. It's just a specific case where A and B are equal, and so the slope that we're looking for is 0. So we had the mean value theorem, we have Rolle's theorem, we also had the extreme value theorem. The extreme value theorem said, okay, if you've got a graph and it's continuous, it goes from A to B, there is guaranteed to be a minimum value and a maximum value on every closed interval for a continuous function. That's all the extreme value theorem says. And what it says is that you can find those minimums and maximums by plugging in the endpoints to the original function, and also by plugging in any critical numbers, right? Because remember, your function could do something like this. Go to the next slide here. So if I'm looking on the interval from A to B, I want to test those endpoints. I'm going to plug those into f of x. But then I also want to check any critical numbers. I want to check here, and I want to check here, right? And so you're plugging all of those, let's say that's C, that's D. So you're plugging in your endpoints, you're plugging in all your critical numbers, and you're just looking for the highest number, right? You're looking for the highest number for the maximum, you're looking for the lowest number for the minimum. To get those critical numbers, to find these points that you want to check with the extreme value theorem, this is where you're setting the derivative equal to 0. Remember, your critical numbers are where the derivative is equal to 0. The derivative is telling you that slope, and at any of those maxes and minimums, that's where your slope is literally 0. So that's what we're checking for. So you can do this, you can do the extreme value theorem, or you can do the first derivative test. They will tell you the same information, right? So you can do the extreme value theorem, check your endpoints and your critical numbers, or you can do the first derivative test. What the first derivative test does for me is it says, okay, if I've got a function that looks like this, here's a critical number. I already know how to find that, set the derivative equal to 0. If the function goes from increasing to decreasing, then I know I have identified a relative maximum. If my function goes from decreasing to increasing, I know I have identified a relative minimum. What you have to watch out for on the first derivative test is you can't just assume that a critical number is going to be a relative min or max, because remember, your function can always do this. There's still a critical number here. There's still a point where the derivative is equal to 0, but it's neither a max nor a min. To find those, what you have to do is you have to set up your table. So this is where you're putting your critical numbers here, and then you're choosing some test values. So depending on what these, let's say this was 1 and 3, I might choose 0, 2, and 5. You can choose whatever numbers you want here, right? You just have to choose numbers that fall between those critical numbers. So choose easy numbers. I choose 0 anytime that I can. And then you plug those numbers into the derivative. And here's the beauty of this. I don't even care what the value of it is. I just need to know, is it positive or is it negative? So if there's no sign change, that tells me the graph was increasing, flattened out, and then it kept increasing. So this critical number is neither. It's neither a max nor a minimum. If my function goes from increasing to decreasing, I know I have identified a relative maximum, and I know that that's now the x-coordinate. I can go plug that into f of x, and I can get the y-coordinate, whatever that happens to be. And I know I found a relative max. If your graph goes from negative to positive, you know you've identified a relative minimum. So let's talk about this. So we have two things here. We've got the extreme value theorem, and then we've got the first derivative test. I just kind of want to compare these two right now. So the extreme value theorem, this is really for when you have an interval. If you're going from A to B, and you're looking for absolute minimum and maximum. You're looking for the absolute minimum and maximum. That's when you want to choose the extreme value theorem. And the reason for that is because the extreme value theorem misses the points that look like this, right? Where it's neither a min or a max, it just keeps going in the same direction. Checking the value of the critical numbers, you miss this piece when you're doing the extreme value theorem. Right? The first derivative test, this is better for when you have the entire function, not just an interval. You're looking at the entire function, and you're looking for relative minimums and maximums. Right? This is going to catch those problem areas, and you're not worried about the endpoints. Right? So if you have a closed interval and you're looking for absolute min and max, that's when you want your extreme value theorem. If you have the entire function, negative infinity to positive infinity, and you're looking for relative minimums and maximums, choose the first derivative test. We also talked about concavity. And so we know this is when it's concave up, this is when your second derivative is positive. If it's concave down, this is when your second derivative is negative. And then we know that if it changes from being concave down to concave up, or vice versa, that point right there is a point of inflection, and this is where your second derivative is equal to 0. We can also use the second derivative test. We've got the second derivative test. This is another way to find relative minimums and maximums. And you can do that by plugging your critical numbers into the second derivative. So you set the first derivative equal to 0 to get the critical numbers. Once you get the critical numbers, then you plug those into the second derivative. So let's say you've got, critical number C. If you take the second derivative of that critical number and it's positive. Again, I don't care what the value is, just if it's positive or negative. If it's positive, you know it's concave up, so you've identified a relative minimum. If it's negative, it's concave down, so you know you've identified a relative maximum. If it's 0, that tells you you're in one of these situations, right, where it's neither a max nor a min. It just changes from being concave up to concave down. You've identified a point of inflection right there. Let's talk about pictures for just a minute. I want you to consider what these derivatives mean, what higher order derivatives mean. So let's say I've got f of x here, and it looks like this. Draw this carefully. And I am asked to sketch f prime of x and f double prime of x. Let's say I'm asked to sketch both of those. I'm going to look for some distinguishing features of my first derivative, because remember what the derivative tells me. It tells me the slope. And then the second derivative tells me the concavity, and it tells me the slope of the first derivative. Right? Every time you take a derivative, you're finding the slope of the previous function. So when I go look at my original function, the first thing I'm always looking for is where are my critical numbers? Where is the derivative equal to 0? And so I'm looking for places where it turns around, it's got a relative min and max. If I have a slope of 0 right here, then I know that those are zeros on my first derivative. Something else I notice here is that it changes from concave down to concave up right here at the origin. That's where my second derivative is going to be 0. So I've already got some points here. That's pretty good. Now I'm going to look at, so what did I just say here? I said this was concave down. That tells me that the second derivative is negative. So to the left of the origin, it was concave down, so I know that whatever I draw here, it's going to be negative. To the right of the origin, it was concave up, so I know my second derivative is positive. So I know I'm going to be in this region here. I can do the same thing with my slopes for the first derivative. Here, the function is increasing, so I know it's going to be positive. Here, my function is decreasing, so I know it's going to be negative in this whole region. Then it goes back to increasing, so it's positive. This is kind of giving me the outline of where I'm going to draw my functions here now. If I have any intuition, if I can recognize that this is a cubic graph, then I know that my derivative should be quadratic. And there it is. And likewise, if I take the derivative of a quadratic, I should end up with something linear. And there it is. So this is kind of my process for sketching those derivatives from the original graph. First thing I'm looking for are critical numbers. Then I'm looking for points of inflection. And I'll go ahead and plot those points. Once I've plotted those points, it really helps me to sketch out, okay, is it above the x-axis or is it below the x-axis? If it's concave down, then I know where I can put my second derivative. Concave up, I know where I need to shade. And then is it increasing or decreasing? That tells me whether it's going to be positive or negative in the first derivative. And then I just kind of follow the map that I've made. I know it's got to pass through this point. I know it's got to go from positive to negative. And if I know what the function is, then I've got an idea of how to shape my graph. Okay? And then the last thing that we talked about were optimization problems. Love these. And so remember, with an optimization problem, the first thing that you need is the primary equation. That primary equation contains the variable that you want to optimize, that you're either finding the minimum or the maximum value for that variable. And what I want to stress to you now is that this is not a related rate problem. In a related rate problem, it didn't matter what this equation was, we could take the derivative of it because we were going to do it implicitly with respect to time. There's none of that in an optimization problem. You can only have one variable, and we have to take the derivative with respect to that variable. So if the primary equation has more than one variable, you need a secondary equation. You need that secondary equation to substitute in to the primary equation to get down to one variable. That's the point here. For an optimization problem, you have to get down to one variable. So there's always the primary equation. It's usually a geometric formula, something like that. And then read that problem really carefully. It's giving you some clue for the secondary equation. You sub that into the primary equation, get down to one variable, then take the derivative with respect to that variable. Once you've got the derivative, you can solve for the critical numbers. So you're taking that derivative, setting equals 0, find your critical numbers. If you have to make a chart, go ahead and make your chart. And then here's the biggest thing with these optimization problems. You've got to check your answer against the context of the problem, right? A lot of times we end up with a positive and a negative solution, but we're talking about real life things here, dimensions of a box. We can't have negative dimensions of a box. So that's the biggest thing with these optimization problems. Get down to one variable, find your critical numbers, find your minimum and maximum, but then check your answer in the context of the problem. Make sure it makes sense in real life. And then also one more thing on these optimization problems is the major shortcut that comes up an awful lot is if you are trying to minimize or maximize a square root function, don't even worry about the square root itself, just worry about what's underneath it. If you minimize or maximize what's underneath the square root, then you've automatically maximized the entire thing. That's going to make derivatives so much easier if you just ignore the square root. Okay, so that's the last shortcut there. If you're doing an optimization problem and you have a formula with a square root, ignore the square root. Just minimize or maximize whatever is underneath that radical. I believe that's everything.